sketch the graph of the function f of x equals x minus 3 times x plus 1 cubed by determining the parts a through I. F of x equals x minus 3, a polynomial, the domain will be all real numbers, times x plus 1, another polynomial, raised to an integer power 3, which will make it a polynomial, so it also will have a domain of all real numbers. And for part A, the domain is all real numbers, or negative infinity to positive infinity. For part B, we want to determine whether there is any symmetry. This is done by evaluating f of negative x and comparing it to the original function f of x. F of x is a product of two polynomials. The first is made up of an odd power of x, this is an implied first power, which will have origin or odd symmetry, subtracting a constant, which always has y-axis or even symmetry. Since the two do not match, f of x will have no symmetry. The same thing's going on with the second polynomial. It's an implied first power, it'll have origin or odd symmetry, and it's added to a constant, which has y-axis or even symmetry, and the two also do not match. F of x will definitely have no symmetry. F of negative x is negative x minus 3 times negative x plus 1 cubed. We can factor a negative out of the negative x minus 3, which will leave behind x plus 3. And we can factor a negative out of the negative x plus 1, which will leave behind x minus 1. The entire quantity is cubed. A negative cubed will be a negative. It can move out front with the other negative to become positive. There is an x plus 3, and there is an x minus 1 quantity cubed. Comparing this result to the original, the x's have the same sign, but the constants have opposite sign. Since the constants have opposite sign, this does not equal the original function f of x, and it will not have y-axis or even symmetry. Since the x's are the same sign, it will not equal the negative of the original function, and it will not have origin or odd symmetry. So for symmetry, it will have none. For part C, we want to determine the y-intercept. This is the point where the graph crosses the y-axis, defined by x equals 0. We can find the corresponding y-coordinate by plugging the x-coordinate 0 back into the original function, y equals f of 0, which is 0 minus 3 times 0 plus 1 quantity cubed. 0 minus 3 is a negative 3. 0 plus 1 is 1, and then quantity cubed. 1 cubed is 1, and negative 3 times 1 is negative 3. We have an x-coordinate of 0. We find a corresponding y-coordinate of negative 3. For part D, we want to determine the x-intercepts. These are the points where the graph crosses the x-axis, defined by y equals 0. Y, which is f of x, will be set to be 0, and we can solve for all x's. It's best to have the function fully factored. It already is. Since it's fully factored, we can see the solutions x equals 3 from the x minus 3 factor, and x equals negative 1 from the x plus 1 factor. The y-coordinate is 0, and these are the corresponding x-coordinates. So we have 3, 0, and negative 1, 0 as the two x-intercepts. For part E, we want to determine any vertical asymptotes. F of x is a product of two polynomials and has no denominator, so there will be none. For part F, we want to determine if there are any holes in the graph. F of x has no denominator, so there will be none. part G, we want to determine any end behavior, horizontal asymptotes or slant asymptotes. F of x is a product of two polynomials and has no denominator, so there will be no horizontal asymptotes or slant asymptotes. But because f of x is a product of two polynomials, which will be another polynomial, it will have left end and right end behaviors of positive infinity or negative infinity. We can determine the left end behavior by taking the limit as x approaches negative infinity of the function x minus 3 times x plus 1 cubed. Only the highest power terms in each of the polynomials will matter here. X and x cubed. Plugging in negative infinity times negative infinity cubed. Negative infinity cubed will be negative infinity times negative infinity will be positive infinity. X times x cubed is x to the fourth, and negative infinity to the fourth will be positive infinity is another way to look at it. The right end behavior can be determined by taking the limit as x approaches positive infinity of the function x minus 3 times x plus 1 cubed. Only the highest power terms in each of the polynomials will matter. You have an x and an x cubed. Positive infinity times positive infinity cubed. Positive infinity cubed will be positive infinity times positive infinity will be positive infinity. For the highest power terms, x times x cubed is x to the fourth, which is an even power. And if the highest power term is an even power, the signs of the infinity on the left end and right end behaviors will match. They are both positive infinity here. For part H, we wanted to determine the intervals of trend, relative maxima, relative minima, plateaus, and cliffs. All of this involves the first derivative, f prime of x. Taking it right from f of x is a product of two polynomials, so f prime of x will require the product rule. It'll take a little bit of room to work out the derivative here, so we can work it out on another page. F of x is x minus 3 times x plus 1 cubed. So the derivative, using the product rule, will be the derivative of the first, which is a 1, times the second left alone, x plus 1 quantity cubed, plus the first left alone, x minus 3, times the derivative of the second, which is a power rule. Bring down the power, leave the inside alone, subtract 1 from the power, and then multiply by the derivative of the inside to complete the chain rule. The first term is 1 times an expression. 1 times anything is the same thing, so it'll be x plus 1 cubed. For the second term, we can bring the constants together. There's a 3 and a 1. 3 times 1 is positive 3. So plus 3. There's an x minus 3, and there's an x plus 1 squared. We want to fully factor the first derivative. There is a common factor of the lower power of the powers of x plus 1. The lower power will be the 2. So we can factor out x plus 1 to the power of 2. Factoring is division. Division is subtraction of exponents. By factoring out an x plus 1 to the power of 2, we will be subtracting a 2 from each of the powers. From this power, if we subtract a 2, it becomes a power of 1, and we have x plus 1 to the first power, or just x plus 1. If we subtract 2 from this power, it'll become a power of 0, and anything raised to 0 is a 1, and what's left is 3 times x minus 3. There's what's left after factoring. So it will be an x plus 1 and a 3 times x minus 3. So we have an x plus 1 quantity squared. In the square brackets, we can remove the parentheses from the x plus 1, distribute the implied 1 into it, which will just keep it as an x plus 1. And we can distribute the positive 3 and the x minus 3, which will give a positive 3x and a minus 9. We can now combine like terms together. I'm going to turn the square brackets into parentheses again. X plus 3x is 4x. 1 minus 9 will be negative 8. This can factor a little further. It has a common factor of 4. That 4 will move out to the front of everything. Factoring a 4 out will leave behind an x minus 2. I'm going to write this in order with the x minus 2 first, just because it's a lower power by being quantity to the first power, and then the x plus 1 squared. There's the first derivative, fully factored. So it was 4 times x minus 2 times x plus 1 quantity squared. Since we have the first derivative fully factored, we can now set the numerator equal to 0, and the denominator, if there is one, also equal to 0, and solve for all x's. Since it's fully factored, we can see from the x minus 2 factor we get x equals to positive 2. From the x plus 1 factor, we get x equals to negative 1. We'll now check to see which of these are in the domain. The domain is all real numbers. X equals 2 is a real number. X equals negative 1 is a real number. They are each in the domain. They are each a critical number. We can now draw a domain line, a line representing the domain. It has no left end because it begins at negative infinity, and it has no right end because it ends at positive infinity. We can put all critical numbers on here in order. Negative 1 comes before 2. This splits the domain interval into 3 separate intervals. We can pick a test value in each interval. The first interval, negative infinity to negative 1, contains negative 10. The next interval, negative 1 to positive 2, contains 0. The next interval, 2 to positive infinity, contains positive 10. We can test the trend in each of the intervals by plugging the test value back into the first derivative. We only care whether it is positive or negative. So the best place to plug in is the fully factored version. A couple of things about this. The 4 at the beginning is positive, and the x plus 1 is to an even power, and therefore also will always be positive. And so neither of those will determine whether f prime of x is positive or negative. Only the x minus 2 will determine that. We only need to plug into the x minus 2. Plug in the test value of negative 10. Negative 10 minus 2 is a negative. We have a negative first derivative. This corresponds to a decreasing trend. Plugging in the test value of 0. 0 minus 2 is negative. We have a negative first derivative. This corresponds to a decreasing trend. Plugging in the test value of 10. 10 minus 2 is positive. We have a positive first derivative. This corresponds to an increasing trend. Right at the critical number of x equals negative 1, we have the trend on the left decreasing, and the trend on the right also decreasing. The trend didn't change. Yet x equals negative 1 is a critical number, and it came from the numerator. Therefore, x equals negative 1 will be a plateau. It has an x-coordinate of negative 1 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of negative 1, which is negative 1 minus 3 times negative 1 plus 1, and then quantity cubed. Negative 1 minus 3 is negative 4. Negative 1 plus 1 is 0 cubed. 0 cubed is 0 times the negative 4 will be 0, so we have a corresponding y coordinate of 0. It turns out this was one of the x-intercepts from up above. Right at the critical number of x equals 2, we have the trend changing from decreasing to increasing, so x equals 2 will be a relative minimum. It has an x-coordinate of 2, and it has a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. Y equals f of 2, which will be 2 minus 3 times 2 plus 1, and then quantity cubed. Two minus 3 is a negative 1. 2 plus 1 is 3 cubed. 3 cubed is 27 times the negative 1 will be a negative 27. So it has a corresponding y-coordinate of negative 27. For part I, we want to determine the intervals of concavity and any inflection points. All of this requires the second derivative, f double prime of x. We will take this from the first derivative. The first derivative is a product of expressions, so it too will require a product rule. And we can work it out on a separate page here. So f double prime of x equals, if we take it from here, it'll just be a product rule of those expressions, and that constant 4 will just come along with the result. So we have 4 times the derivative of the first, which will be a 1, times the second left alone, x plus 1, and then squared, plus the 4 times the first left alone, times the derivative of the second, which is a power rule. Bring the power down, leave the inside alone, subtract 1 from the power, it'll now be to the first power, and then multiply by the derivative of the inside to complete the chain rule. For the first term, we can multiply the constants. 4 times 1 will be a 4. We have an x plus 1 squared. For the second term, we can multiply the constants. 4 times 2 is 8, times 1 is still 8. We have an x minus 2, and we have an x plus 1. We want to fully factor the second derivative. There's a common factor from the constants of 4. So we can factor a 4 out. And there are powers of x plus 1 to the 2, and x plus 1 to the implied 1. We can factor out the lower power of the 2. That'll be x plus 1 to the 1, or just x plus 1. Factoring out the 4, this will become a 1. This will become a 2. Factoring out the x plus 1 to the first power, factoring is division. Division is subtraction of exponents. We're going to subtract 1 from this power. 2 minus 1 will become a 1. And we will subtract 1 from this power. It's an implied first power. 1 minus 1 is 0. The entire thing's to 0. The entire thing's a 1. So there's what we have left. 1 times x plus 1, or just x plus 1, plus 2 times x minus 2. So we have a x plus 1 plus 2 times x minus 2. So we have a 4. We have an x plus 1. Inside the square brackets, we can distribute the implied 1 to the x plus 1 in the parentheses, which will just be x plus 1. Come out of the parentheses then. And we can distribute the positive 2 into the x minus 2, which will be plus 2x minus 4. So inside the square brackets, we can combine like terms. I'm going to turn the square brackets into parentheses now. X plus 2x will be 3x. Positive 1 minus 4 will be negative 3. We can factor the 3x minus 3 a little further. It has a common factor of 3, which will factor out and move out with the 4 to become a 12. We have the x plus 1, and then factoring a 3 out of 3x minus 3 will leave behind x minus 1. There's the second derivative fully factored. So it is 12 times x plus 1 times x minus 1. Now that we have the second derivative fully factored, we can set the numerator equal to 0 and the denominator, if there is one, also equal to 0. Solve for all x's. The x plus 1 factor will give x equals negative 1. The x minus 1 factor will give x equals positive 1. We'll check to see which of these are in the domain. The domain's all real numbers. X equals negative 1 is a real number. X equals positive 1 is a real number. They are both real numbers. They are both in the domain. They are both candidate numbers. We can now draw a domain line. It has no left end because it starts at negative infinity, and no right end because it ends at positive infinity. We can put all candidate numbers on here in order. Negative 1 comes first, then positive 1, which splits the domain interval into 3 separate intervals. We can pick a test value in each of the intervals. The first interval, negative infinity to negative 1, we can pick negative 10. The next interval, negative 1 to positive 1, we can pick 0. The next interval, positive 1 to positive infinity, we can pick positive 10. And we can test the concavity in each of the intervals by plugging the test values back into the second derivative. We only care whether it is positive or negative. So we'll plug into the fully factored version, which is this here. For this one, only the 12 is guaranteed positive and will not affect the sign of positive or negative for the second derivative. But we do need to plug into both the x plus 1 and x minus 1. Either of those can be positive or negative. So plugging in the negative 10 to the portion of the second derivative that matters, negative 10 plus 1 is negative. Negative 10 minus 1 is negative. Negative times negative is positive. We have a positive second derivative. This corresponds to concave up. Plugging the test value of 0 into the portion of the second derivative that matters, 0 plus 1 is positive, 0 minus 1 is negative. Positive times negative is negative. We have a negative second derivative. This corresponds to concave down. Plugging the test value of positive 10 into the portion of the second derivative that matters, 10 plus 1 is positive, 10 minus 1 is positive. Positive times positive is positive. We have a positive second derivative, which corresponds to concave up. Right at the candidate number of x equals negative 1, we have the concavity changing from concave up to concave down. So x equals negative 1 will be an inflection point. It has an x-coordinate of negative 1 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of negative 1. Which will be negative 1 minus 3 times negative 1 plus 1 quantity cubed. Negative 1 minus 3 is negative 4. Negative 1 plus 1 is 0 cubed. 0 cubed is 0 times negative 4 will be 0. It has a corresponding y coordinate of 0. No surprise that this was the coordinates of the inflection point, because back here for the first derivative information we found a plateau there, and plateaus are always inflection points, so it should turn out that way, and it did. Right at the candidate number of x equals positive 1, we also have the concavity changing, this time from concave down to concave up. So x equals positive 1 will also be an inflection point. It has an x-coordinate of positive 1, a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. Y equals f of 1, which will be 1 minus 3 times 1 plus 1 quantity cubed. 1 minus 3 is negative 2. 1 plus 1 is 2, and then cubed. Which will be negative 2 times 2 cubed is an 8. And negative 2 times 8 is negative 16. So we have a corresponding y-coordinate of negative 16. We can now graph the function. We have a vertical axis. We have a horizontal axis. The domain is all real numbers, so all x values will be represented here. We have no symmetry at all. We have a y-intercept of 0, negative 3. That'll be in here somewhere. We can label this. We have x-intercepts at 3, 0 and negative 1, 0. We can label these. We have no vertical asymptotes, no holes. We have left-end behavior of positive infinity. That means that the graph on the left end ends up here. And we actually have right-end behavior also positive infinity, so at the right end of the graph it also ends up here, so we'll be sure it does follow that. Right at negative 1, 0, which is one of the x-intercepts, we do have a plateau occurring there. And if we look, it's a decreasing type of plateau. It's decreasing on both sides. So that means we'll have a shape something like this. A decreasing, it goes to a horizontal there and then turns like so. Decreasing on both sides. It's also an inflection point, and it's concave up on the left and concave down on the right. And it is following exactly that as it should. right at the point 2 comma negative 27, we should have a relative minimum. That'll be down here. We can label it. And it'll have the shape of being a relative minimum, something like that. We've already accounted for the plateau inflection point at negative 1, 0. We should have an inflection point at 1 comma negative 16. That's going to be somewhere in here. And that's going to be concave down on the left of it. So it's got that curving downward sort of effect going on here, like so. And to the right of it, it's going to stay concave up from then on. And we can see it changing over to now being curving upward. And it will continue to do that after. We can label that point. It is 1 comma negative 16. Or in that we can put in the remainder of the graph. This passes through this point. And it does end up at positive infinity on the right end, as it should. And we'll finish it off over here. And we actually have it ending up at positive infinity on the left end as well. It does follow the end behaviors as it should. It covers the entire domain of negative infinity to positive infinity for x's. Everything is being met here. This will represent the graph of f of x.